Okay, hello, basic electricity class. This is, what's today? Wednesday, September 30th. Our lecture for today is going to be recorded. So if you have any questions, you can go ahead and email me. I will be available through email. So I'm going to get started. Today we are going to talk about DC measuring instruments. This is probably going to be a review for many of you. We'll talk a lot about ohm meters, ammeters, voltmeters, multimeters, and the use of them. And then a little bit more in detail of where they came from and how they operate. These are the pages that you can refer to in your FAA handbook. So we'll talk about DC measuring instruments, Darsonoval's meter movement, current sensitivity and resistance, damping, electrical damping and mechanical damping, basic multi-range ammeter, and some precautions when using these instruments. Analog meters. Analog meters are characterized by the fact that they use a pointer and scale to indicate their value. An example of reading an analog meter is similar to reading a speedometer meter on your fuel gauge in your car. Darsonoval meter movement. This is one of the common types of meters. The Darsonoval movement operates only on DC currents or rectified AC currents. And here's an image of your Darsonoval meter movement. You have your permanent magnet, your pointer with your coil spring here, and your moving coil. Basic Darsonoval meter movement with rectifier to change AC voltage to DC voltage. So you have an example of that here as well, picture, just so that you guys have an idea of what those things look like. We'll be going over rectifiers and stuff like that. I think that's in advanced electricity. Yeah, rectifiers are in advanced electricity. But we will be going over AC voltage in probably a week or so. Measurement sensitivity. Measurement sensitivity is the current sensitivity of a meter movement is the amount of current required to drive the meter movement to a full-scale deflection. This is a description that came right out of your FAA handbook. So an example of this, if we have a meter movement that has 1 milliamp sensitivity, this indicates that the meter movement requires 1 milliamp of current to move the needle to a full-scale indication. Similarly, if we have a half-scale deflection, would require only half a milliamp of current. The movement resistance is the actual DC resistance of the wire used to construct the meter coil. In a standard Darsonoval meter, movement may have a current sensitivity of 1 milliamp and a resistance of 50 ohms. If the meter is going to be used to measure more than 1 milliamp, then additional circuitry is required to accomplish this. And that would be a shunt would be required, and shunts we will be covering in advanced electricity. So just understand what meter measurement sensitivity is and what that means for your instrument. Deflection. So here we have a diagram demonstrating deflection in meter movement. The deflection of the instrument provides a basis for determining the quantity under measurement. The measured quantity produces some physical effect with deflects or produces a mechanical displacement of the moving system of the instrument. An opposing effect is built in the instrument which tries to oppose the deflection or the mechanical displacement of the moving system. The opposing effect is closely related to the deflection. The opposing effect is so designed that its magnitude increases with the increase of deflection. The balance is achieved when opposing effect equals to cause producing the deflection. The value of measured quantity can be measured from the deflection at the point of balance. The pointer comes to its correct position on the application of the deflecting torque. The pointer returns to the zero position when the deflecting torque is removed. The control torque is obtained by either two spirally wound springs or a twisted suspension wire. So this is just a larger image of that same image from a few slides ago when we begin to talking about deflection. So you can see these things here that it's talking about. You have your spring in here where your indicator needle is. This is showing you your current through your wire coil, which causes needle to deflect. And you have your meter terminal connections here. And this is showing you your magnet and this area of deflection and your needle. Damping. Damping is the prevention of the oscillations of the pointer to reduce its settling time. So the torque applied to the damped out the oscillations is called damping torque. The methods commonly used for damping can be eddy current damping, air damping or air friction damping, also fluid damping or fluid friction damping. Eddy current damping. I'm not going to cover eddy current damping because eddy current is covered in our class that goes over non-destructive testing. So for basic electricity, we are not going to get into eddy current. But we will discuss air damping. So air damping is when the piston moves into the chamber, the air chamber. The air inside is compressed and pressure of air builds up. This opposes the motion of the piston. When the piston moves out of the chamber, the pressure in the closed space falls, and the pressure in the open side is greater than the other side. The pressure on the compressed side is more than that on the other side. This opposes the motion of the vane and slows down its movement. And here's a diagram of that. So you have your air chamber right here, your piston, and using that for damping shows you how this operates with the pressure when it's greater on one side than the other. So that's going to help dampen your indicator. And this is to aid in oscillations when your pointer is trying to settle. This would be on analog instruments. So if you have an analog meter, ohm meter, multimeter, whatever, it can use air as a form of damping. We can also use fluid damping. Fluid friction damping oil is used in place of the air. The viscosity of the oil is greater. The damping force is also correspondingly greater. So we get a better damping force when using fluid. When the moving system moves, the disc moves in oil and a frictional drag is produced. The frictional drag always opposes the motion. We have another diagram here explaining that. So we have our damping oil. We have our piston, and this is going to create a frictional drag in our instrument. Instrument errors. The accuracy and precision of an instrument depends upon its design. The material used and the workmanship involved in manufacturing the instrument, which contributes to various types of errors. These errors include gross error, systematic error, and random error. These are just a few that we're going to go over. There's a couple more, but I don't want to get into great detail about instrument error because that's not really the scope of this class. Gross error. This class of error mainly covers human mistake in reading the instrument, recording the data, and calculating the measurement results. The experimenter may grossly misread the scale. So that's gross error. Systematic error. We have a few different types of systematic errors. We can have instrumental systematic error. We can have observational and environmental. If we have a systematic instrumental error, these types of errors take place due to a few different factors, including inherent shortcomings of the instrument itself. It could include misuse of the instrument and loading effect of the instrument. So if we have a systematic instrumental error with due to shortcomings of the instrument itself, these errors are inherent in instruments because of their mechanical structure. So as an example, if a spring used for producing controlling torque of a permanent magnet instrument has become weak, the instrument will always read high. Errors may take place because of friction, hysteresis, or backlash of gears. So these are just inherent to the use of these instruments. Eventually you have these instruments so long, these reading instruments, and use them, the internal workings of them will degrade. Systematic instrumental error due to misuse of the instrument can occur. The error caused in measurements are due to the fault of the operator rather than that of the instrument. These errors may be cited for this misuse of instrument, may be failure to adjust the zero of the instrument, could be poor initial adjustments, or use of high resistance leads. So these are all things that are categorized as misuse of the instrument. Loading effect. Loading effect errors are committed by beginners using measuring instruments. So here we have an example. If we have a well-calibrated voltmeter, we may give a wrong reading when connected across a high resistance circuit. The same voltmeter may give a more dependable reading when connected across a low resistance circuit. So the loading of those high and low resistances can affect our readings. We have observational error, and this is exactly what it sounds like. It's observational from the observer, and you have a cool little picture here of if we are looking at this reading straight on compared to our point of view from either direction, if we're at an angle, can change it, and this is parallax. Parallax is the main source of observational error. To minimize parallax error, meters are provided with mirrored scale, as shown in this figure, which the mirrored scale is, you can see in the figure from one side of the scale to the other. It's a little hard to read the reading in this image, but it's a pretty simple concept. Environmental error. These errors are due to conditions external to the measuring device, including conditions in the area surrounding the instrument. These may be effects of temperature, pressure, humidity, dust, vibrations, or external magnetic field, also called stray magnetic field. These are all things that are considered environmental errors to the instrument. Random errors. So we'll always have random errors. These errors exist due to unknown causes and occurs even when all the errors have been accounted for. That's why they're called random. Moving on to talking about our ammeters. Ammeters have a low resistance and must be connected in series with a load. Shunts are used to change the value of DC ammeters. I don't need you to know really what a shunt is at this point right now. Just know that that's how it changes the value of DC ammeters. Shunts are covered in advanced electricity. Clamp-on meters read only one conductor at a time. So this is a diagram showing you the shunt in a ammeter. Again, used to set the value of the ammeter. And here you have your little schematic of your basic ammeter. Many electricians or technicians use clamp-on type of AC ammeters. With these clamp-on type ammeters, you can only read one conductor at a time. We don't have any of these in the shop. You may see these out in the field. Some people use them. I don't see them very often. I think they're more popular among electricians, specific electricians, not necessarily AMTs. Ohm meters. The ohm meter is used to measure resistance. There are two basic types, analog or digital. The common VOM, volt ohm milliammeter, contains an ohm meter. An ohm meter should always be readjusted to 0 when the scale is changed. Digital ohm meters. We have digital ohm meters display the resistance in figures instead of using a meter movement. So digital ohm meters compared to our analog meters. Digital ohm meters operate by measuring the voltage drop across the resistor. The ohm meter, whether digital or analog, must never be connected to a circuit when the power is turned on. Very important. Reading a digital meter. Many digital meters are auto-ranging, which means that they select the range scale automatically. This type will display a notation beside the numerical digits to indicate the meter scale. I don't have a picture for that for you guys. It probably would be good if I did. But I'm not sure what type of ohm meters you guys are using. I mean, Fluke is the best because it is auto-ranging. It's the easiest to read. But if you don't have an ohm meter that's auto-ranging, you need to make sure that you're picking the right scale for what you're measuring. Voltmeters. We have our handy little picture of our voltmeter connected to our battery. The voltmeter is designed to be connected directly across the source of power. And these are a couple of electrical schematics just showing the difference between our digital ohm meter and our digital voltmeter and what they are reading. We also have voltage testers. Our low impedance voltage tester has a very large current draw compared to other types of voltmeters and should never be used to test low power circuits. We should always use the appropriate meter to test the appropriate circuit. So if we want to test a low power circuit, we'll use a voltmeter. Low impedance testers has an impedance of 5,000 ohms and can generally be used to measure voltages as high as 600 volts. These are also known as solenoid type testers. This tester is not susceptible to giving the misleading voltage readings caused by high impedance ground paths or feedback voltages. High impedance ground paths can produce misleading voltage readings. Here you have your schematic of your circuit with your transformer. You have your voltmeter in here to ground. Low impedance voltage tester. Just another diagram for you guys to see the coil to the probes here, and your plunger and spring. A few precautions. When dealing with meters, when using ammeters, always connect ammeters in series with the element through which the current flow is to be measured. Okay, ammeters always need to be connected in series. Never connect an ammeter across a source of voltage, such as a battery or a generator. There should be no reason that we would ever need to connect an ammeter across a source voltage. The only reason you need to do that, you would be using a voltmeter. Remember that the resistance of an ammeter, particularly on the higher ranges, is extremely low, and that any voltage, even just 1 volt, can cause very high current to flow through the meter, resulting in damage. Especially some of your cheaper meters, you'll see that your fuse will blow very quickly if you do this. And very easily, it doesn't take much. Another precaution, use a range large enough to keep the deflection less than full scale. The most accurate readings are obtained at approximately half scale deflection. Many milliamp meters have been ruined by attempts to measure amps. Choose proper scale before connecting the meter in the circuit. And lastly, always observe proper polarity in connecting the meter in the circuit. Current must flow through the coil in a definite direction in order to move the indicator needle upscale. Current reversal because of incorrect connection in the circuit results in a reversed meter deflection and frequently causes bending of the meter needle. Avoid improper meter connections by observing the polarity markings on the meter. Okay, and that's it for lecture today. I know I went through that really fast, but there's a lot of information in here. I know that you guys, some of this is probably review for many of you, just operation of meters and a little bit of how they work and what makes them work. So don't forget to take the quiz tonight by midnight, and the slides will be available tomorrow. So make sure you watch lecture in order to be successful in the quiz. And let's see, what's today? I will see you guys in lecture on Monday, and you will see Mr. Kimball for lab tonight at 5:30. Okay. Thank you. You guys can text me or not text me. You can email me if you have any questions about tonight's lecture.